Alrighty folks, welcome back to AP Chemistry. This video is going to be on bond enthalpies and how to determine the enthalpy of a reaction from the different bond enthalpies that you have. Alright, so the delta H of reaction is going to be equivalent to the sum of all the energy it takes to break all the bonds that will be broken and all the energy that is released from all the bonds that you're going to make, alright? So that's the basic formula you need to know. And yeah, let's try a couple of practice problems. Okay, so if I have two nitrogen molecules, which are going to look like this, okay, that's what the nitrogen molecules will look like as a Lewis structure. All right, what is the delta H of reaction? Well, the way you're going to do this is we're going to determine all the bonds that we're going to break. Now on this side we have two separate molecules, okay? So because we have two separate molecules, we're not actually going to be breaking any bonds. We're going to be solely making bonds here, okay? Now nitrogen has 5 electrons and it's going to share 3 electrons because it wants to get to 8. So it's going to share 1, 2, 3, and then nitrogen goes 1, 2, 3, and it's going to have, they're each going to have a lone pair. So they're each going to form 3 bonds, all right? So, since we're only making one molecule, because we're just going from 2N to 1 diatomic N, we're just going to have this molecule, okay? So that's going to be a total of 950 kilojoules per mole reaction that will be released. And because when we form new bonds, energy is released, it's going to be an exothermic process, so delta H will be negative 950. All right, so this question is going to be a little bit more difficult because we're actually going to be breaking and making bonds here. So it's going to be a little bit more difficult of a question, but it should be just as doable. So if you want to pause the video now and give it a go yourself, I recommend you do that. And then I'm going to show you guys how to do it. All right, so I'm going to draw the structures for each of these molecules. So we're going to have C, which will be double bonded to another C, because carbons have to form 4 bonds when they're in a hydrocarbon. And this will be the structure of CH4. And then we have hydrogen in the gaseous state, which is the natural state of hydrogen. And that just looks like this. All right, so let me show you what is actually going to happen here. Okay, so this is basically what the structure for C2H6 is going to look like. And it's going to be a saturated hydrocarbon because there are no double bonds and the H's have bonded. So the double bond between the carbons is going to be broken so that the electrons are free to be on the outside of the carbons. So we're going to be breaking that double bond and we're going to be breaking this bond between the hydrogens. So because we're breaking 2 bonds, we're going to need to put in energy in order to break the 2 bonds. So we're breaking a carbon-to-carbon bond, so that's going to be 602, okay? And that's going to be positive 602. And then we're going to be adding 436 because that's the amount it takes to break the hydrogen-to-hydrogen bond. Now, this entire equation, we're going to subtract the amount of energy that is released when the next bonds are actually formed. So we're going to be forming a carbon-to-hydrogen bond and another carbon-to-hydrogen bond right there. So we're going to be forming 2 C to H bonds, which is going to release 826 kilojoules each. So I'm just multiplying 2 by 826 and putting that all into my calculator. So that gives us a negative 614 kilojoules per mole reaction. And that's going to be what delta H is equal to. All right, so here's one more problem for you guys to try. I recommend you guys try it out on your own, and then I will do it with you guys. So I'm going to draw out the structures for each of these like I did last time. Oxygen in the gas state just looks like that. And then we have 2 gaseous hydrogens, which will just look like this, okay? And then we're forming 2 H2Os, which will look like this. So basically, here's what's going to happen. I'll show you this. So putting it into blue, we're going to be breaking this bond here between the oxygens because we need 2 separate oxygens like you see over there, okay? So we're breaking that bond between the oxygens, and now we have 2 free-flying oxygens. Now, we're going to be breaking each of the bonds between the hydrogens so that the hydrogens can each individually bond the oxygens like you see I'm drawing there. So we're going to be breaking 2 hydrogen to hydrogen bonds and 1 oxygen to oxygen bond, okay? So let me just erase this, get this out of the way, and I'll show you what's going to happen numerically. Breaking the oxygen to oxygen bond is going to require 146 kilojoules of energy, and that's positive. And then we're going to be adding 2 times the hydrogen to hydrogen bond energy. So that's 436 kilojoules. And then we're going to be subtracting the bonds formed. So the bonds formed here are going to be, in each molecule, 2 oxygen, 2 hydrogen bonds, which I've just circled very inconveniently for you guys. So 2 oxygen, 2 hydrogen things. And there are 2 H2O molecules, so I'm just going to put a 2 there. And then we have oxygen to hydrogen is going to release 463 kilojoules I. And let me just put that into the calculator for you guys. So delta H reaction equals 834 kilojoules. And that's negative because the process is exothermic. And that's basically bond enthalpies for you guys.